Welcome to the course on two-dimensional signal processing, principles and practices. We'll do the 2D Z transform from the extension of this 1D Z transform. So 2D Z transform has for a sequence x of n1, n2 is represented as capital X Z1, Z2. So the representation is similar to the 1D Z transform where it is x of z, only one variable. Here we have these two variables z1 and z2, as we have the two variables in the independent variables in the time domain as well. So x of n1, n2, the Z transform is capital X of z1, z2, which is defined like that. The summation varying from n1 minus infinity to plus infinity, n2 varying from minus infinity to plus infinity, x of n1, n2, z1 power minus n1 and z2 power minus n2, where z1 and z2 are the complex variables. And these complex variables spans in 2D space. So z has real of z and imaginary of z, whereas z1 has real and imaginary of z1 and z2 has real and imaginary of z2. So if you take the z plane, real z and imaginary z for 1D sequences Z transform, whereas here we have four variables. So real of z1, real of z2, imaginary of z1 and imaginary of z2. So this is considered to be in the 2D space. So this variable spans over in the 2D space. Actually it is, because of 2 in each, it is a four-dimensional space. Okay, so four-dimensional space too difficult to visualize. So we'll see in the case of row C, so how this z1 z2 can be visualized in terms of 2D space. So with the Z transform of the 2D, x of z1, z2 is evaluated, suppose, into r e power j omega 1, r e power j omega 2, r1 and r2 can be, or r is taken as 1 here. So z1 equal to e power j omega 1 and z2 equal to e power j omega 2. So if we evaluate it, x of n, where this, so z1 and z2, if we take it as this z1 and z2 here, what we had given, so z1 is replaced with e power j and e power minus j omega n1 and e power j omega 2 n2, just replacing z1 with e power minus j omega 1 n1 and e power j minus omega 2 n2, which is the x of omega 1, omega 2, or x of e power j omega 1 e power minus j omega 2 here. So if you recall that we have done this in the case of 2D DTFT or DSFT. So this is nothing but the DTFT of DSFT 2D of x of n1, n2 sequence. So this one is evaluated at z1 e power j omega 1 and z2 e power j omega 2 here. So so that's why it is considered, as we said, in the 1D Z transform as well. It is a generalized version of the Fourier transform. So here R is neglected. If you consider this Z1 in the Z1 equal to R1 e power minus j omega 1, or this case here, and R2 e power j omega 2, Z2 is. So if you take these two things, and this would be x of n1, n2, r power minus n1, r1 and r2 power minus n2, so on. So this would converge, it's a DTFT of the sequence as we did in the 1D sequence as well. So this is evaluated at, this is spanned also into z1 and z2, where r is unity taken as 1. Here also the z1 is 1 e power j omega 1 and z2 is r2 e power j omega 2. r1 and r2 are taken as 1 here, r2 equal to 1. So then it would z1 and z2 it will be span over a 2D space of, that is called the unit space. So we'll visualize that, and it is also say that we have the generalized Fourier transform. Supposing this z1 is r1 and r2 instead of r1 and r2 equal to 1, so then r1 and r2 are the radius and omega 1 and omega 2 are the arguments in the z1 z2 plane. So r was, in 1D case, just to recall, r is the radius and omega was the argument of this z plane. So now here we have the two variables in each, r1 and r2 and omega 1 and omega 2. So the equation now becomes here x of n1 comma n2, the summation is varying from minus infinity to plus infinity for both the variables of n1 and n2, and r1 power minus n1, 2 power minus n2. So this z power minus n1 is replaced with r e power minus j omega 1 and e power minus j omega 2 n2 n1. So this is a case of expanding this. So what is the representation, or what representation it would give here is that x of n1 comma n2, and these two sequences are considered to be the x of n1 comma n2 r1 or minus n1 r2 or minus n2. So for this sequence, this is the dt of t, or the Fourier transform of this. So Fourier transform of this sequence is nothing but x of z1, z2 when it is evaluated at z1 equal to r1 e power j omega 1, z2 is r2 e power j omega 2. So this case is the Fourier transform of the sequence, as we said, and the uniform convergence of this sequence is possible by extending the same concept of 1D, that this needs to be summable. So absolutely summable. So that case is we can take that the magnitude of it should be less than infinity for the summation n1 is varying from minus infinity to plus infinity, and n2 also. So this r1 the magnitude z1 and r2 magnitude z2. So the value of r1 and r2 is defined from the z1 and z2 here. So it needs for the convergence, it needs to have the absolute summability of x of n1 n1 into r1 r2 over this. So it generally depends on the value of r1 and r2. So that's how we define the case of range of r for which this is possible, is defining the ROC, region of convergence. So we'll see the region of convergence here with r1 and r2 in the case of this. Supposing we take an unit step sequence u of n1 comma n2, in that the absolute summability will have this x of n in the previous summation is replaced with y u of 1 u of n1 comma n2, and it is absolutely summable only for z1 greater than 1 and z2 magnitude greater than 1. So in that case, so this can be only defined for these r1 and r2 values of this 1 and 1, z1 is greater than 1 and z2 is greater than 1. So this is defining the region of convergence. Now the region of convergence, it is the ROC for which, for the range of r for which it is absolutely summable, or it is giving the summation less than infinity. So we can look at this in the space of z1 and z2 plane, first considering this step sequence. So how do we give the step sequence in the 2D? So if we recall the very first few lectures of the 2D signals, we have plotted the sequences wherein u of n1 comma n2 is the sequence for n1 n2 greater than or equal to 0, this u of n1 comma n2 is 1. So n1 greater than or equal to 0 and n2 greater than or equal to 0, these are the first quadrant sequence. The region of support here is that first quadrant. So this is the sequence for which we compute the Z transform. So x of z1 comma z2, that is 2D Z transform, where n1 is now the limit changed from 0, n2 also limit changed from here to 0, minus infinity to 0, minus infinity, now it has become 0 to infinity and 0 to infinity because the sequence exists in this first quadrant. And u of n1 comma n2 z1 and z2 power minus 1 n1 and minus n2. So this summation, now how can we simplify it? So the case, this is 1, all of the values are 1 here, right? These are 1. And now so z1 is a summation of this n1 here and summation of n2. If you split this, so split the summations of here z2 and z1 from n2 to n1, n0 to infinity and 0 to infinity here. So this can be now brought to the closed form solution because these two are the products here. So the case is 1 by 1 minus z1 power minus 1. So this would be less than 1, z1 power minus 1 should be less than 1 and z2 power minus 1 should be less than 1. So we get the closed form summation 1 by 1 minus z1 power minus 1 or z by z minus 1, z1 minus 1 and z2 by z2 minus 1. So as we did in the 1D. So the region of convergence now comes from these two conditions. So z1 should be greater than 1 and Z2 should be greater than 1. So this cases Z1 greater than 1 and Z2 greater than 1 of the region of convergence. So we have to combine these two to get the ROC of the Z transform. So for the 1D case, like what we did in the case that's a real of Z and imaginary of Z, there were two cases. One was with R1 only one sequence and one is with the left-sided and right-sided sequences. We have both the ones like a two-sided sequence. You will have this kind of R1 and R2 radius, and this can be just represented that Z plane as a point. R1 as one point and R2 is another point, and the shaded region is this. You can represent it like this C. So because this type of visualization is required to do the 2D Z transform region of convergence. Here it is 1D. So for 1D signals, this is typically bounded by these two circles. So the Z plane this origin would be equal to 0. Whereas in case of 2D, what is the Z1 and Z2? We have Z1 and Z2, not real of Z and real of imaginary of Z. Okay, so that would be because we have 2 for Z1 and 2 for Z2, and this is going to be a 4D space. So that it cannot be sketched and visualized. So we can have this ROC depends on this as a 2D sequence, which can be have like the contour map like the ROC. So by plotting it with respect to Z1 and Z2, the conditions now for the case of Z1 equal to 1 and Z2 equal to 1. So we can have the point sketch for Z1 equal to 1 and then Z2 equal to 1. So this values corresponding to your 2D surface, and that this 2D subspace Z1 and Z2 is a subspace of the space of the 4D space is here. If you have the 4D space, in that we just take the 2D space or the 2D subspace from it to represent the ROC. So this is how 2D Z transform ROC is specified. Instead of having these 4 variables variation need not be sketched, we will not be able to visualize it properly, so that we get this 2D subspace of Z1 and Z2. So for the examples of that, we had previous case Z1 and Z2, we had 1 and 2. So this would be the Z1 greater than 1, this is 1 and this is 1 greater than 1. So this would be the ROC for the previous case, like the unit sequence which we had taken. This sequence Z1 greater than 1 and Z2 greater than 1. So that ROC is now we are defining it here. This case is the Z1 greater than 1 is this region, complete region, and Z2 greater than 1 is this region. So when we take the intersection of these two, this is the region which is representing the ROC of the 2D sequence, that is a unit step sequence. Now taking an example of it, compute the Z transform and its ROC of the sequence x of n, a power n1, b power n2, u of n1, n2. So this is also restricted to the u of n1, n2, that is in the first quadrant sequences. So the A we considered this as less than 1 and B also. So that will be an exponential decaying sequence. So that is not a concern here. So we plot the sequence first with because it is multiplied by u of n1, n2. So u of n1, n2 exists in the first quadrant. So this sequence also would exist in the first quadrant. So if you plot the sequence when n1 equal to 0 and n2 equal to 0, so then it would become 1 here. This is the point, and n1 1 and n2 0. So this becomes a1 a, and this is n1 equal to 2 and this is n2 0. So this a square a cube, this point n2 is 0, where n1 is 0, b square b cube. And other values, if both are 1, so this represents AB, and both are 2, a square b square, both are 3 and a cube b cube. So rest of them are as follows: a square b, a cube b, and then a cube b square, a square b cube, and a b cube, and so on. So we get the sequence. This is x of n1, n2 sequence. Now taking the Z transform of it. So n1 and n2 from 0 to infinity, a power n1 and b power n2, u of n1, n2, z1 minus n1 and z2 minus n2. So this can be the clubbed with a1 and z1, that is a and z1. Here a is z1 power minus 1 power n1, and similarly this is one pair and this is another pair, like what we can have b a power n2 and z2 power minus n2. So if we take this to find the closed form solution, a z1 here power minus 1 should be less than 1 and b z2 should be less than 1. Okay, power minus 1 should be less than 1. So this can be written as 1 by 1 minus a, 1 by 1 minus a z1 power. Here what we get 1 by 1 minus a z1 power minus 1, and this would result in 1 by 1 minus b z2 power minus 1. So from that we get the ROCs are z1 greater than a and z2 greater than b. So these cases also a by z is less than 1 and b by z less than 1 here. So this case can be visualized now. Z1, the ROCs are we obtained as Z1 is greater than A and Z2 is greater than B. So Z1 is this representing this and Z2 representing here in the x and y axes. In this Z1 Z2 plane, we have Z1 equal to A, which is this line, and Z2 equal to B is this line. So A and B, and now Z1 greater than A is this region, the complete region here also, this complete region, and Z2 greater than B is this region, completely this region. So here, but the intersection of these two is the particular region which is marked over here, the ROC. So this is again the first quadrant sequence, so which gives the ROC in this fashion. This is not restricted here, this is going beyond the values greater than also. So just to show that ROC, it is given in the square, so it's not bounded by this values or the line. So this is above and completely this region, and then the complete other region, the intersection is the ROC which is marked over here. So Z1A equal to A for any Z2. The Z2 can be any Z2 value. Similarly, it is valid for Z2 equal to B and for Z1 any value. So considering this, the common or the intersection of the two regions are ROC, the region of convergence. So this transform has the ROC of this region. So this can be better visualized with 2D plane, that is a subspace of the 4D space. And 1D poles of x of z, if we compare it with 1D signals, z transform, these are points in the z plane, that is as I told, the ROC is bounded by the poles. What is that? And whereas in the case of 2D signals, this x of z1 comma z2 are 2D surfaces of the 4D z1 z2 space. These are the surface what we had on z1 and z2, the surface what we have got. And 2D ROC is bounded by pole surfaces, not poles exactly, pole surfaces, again to visualize. And taking an example of the other sequence like what we did in the 1D, so A power n1 and B power n2 which has minus, and u of minus n1 minus 1 and n2. So this sequence, now if we plot it, we have the sequence in the n1 is taking the values negative, okay, up to 1. So a minus infinity to 1. So here, and n2 can take any values over here. So because the restriction is based on this, so this is from minus infinity to minus 1. So n2 has u of minus n1 come minus n2 here. So this would be in this region. So it is in the second quadrant. So if we substitute n1 and n2 values on 1 here and n2 0, this would result in minus a minus 1, minus a minus 2, power minus 2, minus a power minus 3, and so on, minus a power minus 3 into b. This is going to be for n2 1 and n2 2, these points we obtain. Minus a1 minus 1 and b square minus a2 minus 2 b square, and so on. So this sequence is now in the second quadrant. Let us see the region of convergence for this sequence. So taking the summation from minus infinity to plus infinity, because this exists in the minus infinity to minus 1 and minus infinity to here plus infinity, this summation would vary minus infinity to minus 1, the first case a z1 power minus 1 n1, whereas n2 is from 0 to infinity, so b z2 power minus 1 n2. So from the sequence. So this can be written like what we did in the minus n equal to m. So minus n1 can be equal to m, and simplify this as we did in the 1D sequence. So what we get is this summation now results in 1 by 1 minus a is z1 power minus 1. So you can see, and this case 1 by 1 minus 1 b is z2 power minus 1. So the two sequences resulting in this similar kind of Z transform here also. So the first case, a is z1 for minus 1 should be, this is less than 1 in the sense for not for minus infinity to minus 1, it is going to be 1 to infinity. In that case, a inverse z1 power minus 1 is less than 1. Okay, so if we change it to m, the negative n indices, so z1 we obtained from this case, the z1 is less than a. So note the change of the left-sided sequence, what we are just extending to the 2D sequences as well. So this is for the left-sided sequence, and this one is for the right-sided sequence where z2 is greater than b. And now the ROC for these two cases, if we plot, that is z1 less than a, z1 equal to a is this line, and z2 is equal to b is this line. So z2 greater than b is this region, complete region, and z1 less than a, that is this region, this total complete this region. So the intersection is here, the ROC, the intersection of these two regions or ROC is different. So it is the second quadrant in the Z plane. Actually here is the second quadrant sequence results in the ROC of Z1 and Z2 in this fashion. So the support surface, the region of convergence is defined in the way. Now the case is Z1 equal to A for any Z2 and z2 equal to b for any z1. So that's why it is for all these regions, but intersection is now only in the second quadrant. So it is, if you recall that Z transform for the first example and the second examples, that it would be same, like, so first quadrant sequence and the second quadrant sequence, both having the Z transform similar, that is same, but only the ROC is different. ROC in the first case, it was z1 greater than a and z2 greater than b, and in this case z1 less than a and z2 greater than b. So the unless until this ROC is specified, it is not, we cannot find it in the unique inverse, like, so ROC needs to be defined for the Z transform, otherwise two different sequences can have the same Z transform. So as we did in the 1D as well as in 2D cases. Now coming to the example of this 3, where x of n1 comma n2, where a power n1, u of n1 comma n2, ut n1 minus n2. So this can be u of 2D also, n1 minus n2. First we'll plot this sequence and then we'll take care of the of a power n1 as well. So the first, this sequence is known, that is a step sequence which carries all the values 1 for n1 n2 greater than or equal to 0, and this 2D n1 minus n2 is that n1 minus n2 is greater than or equal to 0, these values are 1. So in that case it would give the diagonal here, and with respect to the diagonal n1 greater than n2 equal to n1 minus n2 greater than or equal to 0, this would result in 1. So the sequence is this, the second sequence is this. So multiplying these two sequences will result in only this sequence, and this sequence is multiplied with a power n1. So varying this a n1, 1, 2, 3 and so on. So in this way, so we get a sequence which is starting from here. The ones which were here are not going to come in the other x of n1 comma n2 when we multiply them, because this doesn't have the value 1 a square, a square and a square. So this is the sequence what we get for the example x of n1 comma n2. For this sequence, what is the Z transform? So a of power n1, u of n1 n2, ut of n1 minus n2, z power n minus 1 and so on. So we just write it that this is 1 and this is also 1 for certain values. So this summation now from the sequence what we have plotted, n1 and n2 are, n1 is varying from 0 to infinity, that's fine, but n2, if we take, n2 is varying where for the values of n1 only, that is from 0 to n1. n2 0 and to n1. See the limit which is changed over here depends on the sequence x of n1 comma n2, and this a result as such, these two terms would be here. So adjusting this or the summation n1 from 0 to infinity, n2 0 to n1, so which is for this case here, and these two terms would come in this summation. So n1, so now we simplify this n1, and the second summation which we have is the finite summation, and this is n1. So that would be 1 minus z2 power minus 1, n1 the highest limit plus 1 by 1 minus a. So that's the closed form solution for the second case, second part. So we get this and multiply this each one inside this brackets. Here we would get z1 and this summation here and this summation here. Okay, so we get this equation, and from that equation, if the first part is converging to 1 by 1 minus z1 minus 1 z2 power 1, and the second case is here a z1 and z2 power minus n1. So that's how we get 1 by 1 minus a, and this would give us 1 by 1 minus a z1, and this gets simplified. So we get the product of a z1 minus 1 z2. So now what is the ROC for this case? So ROC is defined here, z1 greater than a and z1 z2 greater than a. Well, how do we get this from the, so here this portion needs to be less than 1 and this one should be less than 1. So a z1 z2 should be less than 1. So in that case we get the ROC as z1 greater than a and z1 z2 greater than a. So the common areas, now it is not only z2, so as in the case of previous one, so z2 is depending on z1. So z2 is varying, z2 if you take a by z1, this condition would change to z2 equal to a by z1. So this should not be equal to 0. So that's what z1 is not equal to 0. z1 is a, that is okay for this case, and z2 can be any value that can lead to a line, and whereas this is not going to give a line in the z1 z2 plane, that is going to be a case we'll see z1 z2 plane in which z1 equal to a is this line. So this line which is resulting in the first condition, whereas the second condition z1 z2 is equal to a is that where z2 is depending on z1, z2 is equal to a by z1, right? So this should not be equal to 0. So both are, z2 is inversely proportional, z2 z1 are inversely proportional. So that's why we get this curve which is representing z1 z2 equal to a. So now this needs to be greater than a. So the ROC is, one curve is giving this ROC, and the second this curve which gives the ROC as this one, ROC as this part. So the intersection of these two results in this portion is the ROC of this particular problem. So this also can be represented as one as z1 equal to a by z2. Both are equally valid in this case. So but these two are inversely proportional. So that's why we get the curve which is in the z plane or the z1 z2 plane. We get that ROC as the curve which is of the greater than a. Okay, and this is a line in which this represents a line. So the ROC is this portion. So the sequence x of n1 comma n2 where a or n1 into u of n1 and u 2d of n1 minus n2 gives the ROC as this type of thing. So this is the pole surface representation of the ROC. We had taken the 2D Z transform and we have extended the concepts of the 1D Z transform, like the convergence and the difference between the ROC of where it is a point in the Z plane. Here it is the pole surfaces. The ROC consists of pole surfaces, whereas there it is only poles. Excluding the poles, the region we would get the ROC in the case of 1D. So this 2D visualization, because it is a 4D space, Z1 and Z2 have the two variables, real and imaginary. So we will not be able to plot this with respect to real of Z1 and real of Z2, imaginary of Z1 and imaginary of Z2. It is to have the magnitude of this Z1 and Z2 plane. So then we can at least view the two the pole surfaces as a ROC. So we have seen that this Z transform is same for two different sequences unless until ROC is specified. So for the left-sided sequence and the right-sided sequence, as we did in the 1D Z transform, we have also taken this example in the 2D Z transform, in which the first quadrant and the second quadrant sequences. So first quadrant sequence as well as second quadrant sequence has the same Z transform, but its ROC is different. So unless until ROC is defined, this unique transform is not possible in case of Z transform. So we will do further take few more examples of the Z transform in 2D and how these are helpful in the filter designs, in filter transfer function representation. We will discuss in the next lecture. Thank you.